Okay, so today we are talking about the normal distribution curve. Maybe at some point in time you guys have seen what this curve is, but it is used in statistics, okay, and it is used to basically represent data in different real world types of problems and that, that deal with anything that deals with numbers and calculating means and things like that, okay? So we're going to talk about the normal distribution curve today. Its features, properties, empirical rule, how to use the normal distribution curve to find different probabilities as well. So it does tie into the fact that we've been doing probability since last week. So the normal distribution, sometimes called a bell curve, is distribution of data that occurs naturally in many situations. The most common one that I can think of off the top of my head is test scores. Okay, you know how Mr. Saran and Ms. Dunstan are always looking at like our scores compared to like other schools and things like that. Well, they look at it on a normal distribution curve. Okay, they figure out what the mean was and they compare it to the state, other schools in the county and things like that. Okay, but a very common example of this would be test scores. As you can see, maybe not so well on the board, but maybe on your paper, you guys see that faint line that's like hitting the top of each one of those bars in that bar graph. Okay, that is a normal distribution curve. Okay, it is a bell curve that is asymptotic to an x-axis, which usually represents like test scores or heights or whatever piece of data that you're looking at. Okay, and it's always centered about straight through the mean of the data. Okay, so the mean of the data is always in the middle of your bell curve, of a normal distribution bell curve. Let me be specific. Okay, when data is normally distributed, you basically plot them along the graph, and it results in, like I said, that image there. Now, this is not the only type of bell curve that you can have. Okay, it's not the only type of bell curve that you can have. If you want to take some notes on what I'm about to talk about now, go ahead and flip over to the back. It would be a good place to put it in the notes section. Okay, there's other types of bell curves because not every piece of data is going to be, perfectly centered about the mean. Because if it's like this, that means the mean, the median, and the mode are all the same. Okay, that's what a perfect normal distribution graph is. It's perfectly symmetrical. Okay, all of them are the same. But you can have ones like this, and you can have ones that are like this. Okay? This one right here means that it is negatively skewed. I was going to use the symbol. It's negatively skewed. This one is the opposite. This one means that it is positively skewed. Okay? So basically what that means is that for ones like this, your mean is going to be smaller than your median. So like here, your mean would be smaller than whatever your median value was. And this one would be vice versa. Okay, I can try to add this all into this tiny little slide. Okay, this is helpful in the sense of SAT, ACT, when they start giving you like data and they say, oh, well, is the mean greater than the median? Is the median greater than the mean? And stuff like that. You kind of will want to know this type of relationship. Okay? Yes. And then it would be the opposite. The median would be, the mean is less than the median on the negatively skewed one. And then vice versa on the positively skewed one. Okay? Questions on the two different types. Now, this x-axis, like I said, serves as the numerical values to represent the situation, right? So let's say if this one represented test scores, and let's say your mean was a 70, then that means everything that's bigger, everything that's to the right will be anything that's bigger than a 70, everything to the left will be less than. 70. Okay, so it still works like a regular normal line. Okay, like a normal line. Yes. If it's perfectly symmetrical, it's in the middle as well. But it varies when it's negatively or positively. Now, in such a normal distribution of the data, like I said, the mean, median, mode, they're all the same, okay? And it splits it right down the middle, 50% to the left, 50% to the right, okay? When it's positively skewed or negatively skewed, those numbers change. And it's going to change depending on how the data is spread out, okay? All right. Now, the standard deviation, represented by F, has a different symbol when you get a little to the higher up math. It's the measure of how spread out your numbers are. Okay? How spread out your numbers are. It's related to the normal distribution by the empirical rule. And what you see here, you would definitely want to know. Okay? This symbol, there's an X with a bar over it. It's smack dab in the middle, which means it's called the what? The mean. Okay, so that symbol means mean. The S stands for standard distribution, and they are used when the data is a sample, okay? So for example, if I wanted to figure out what's the mean and the standard deviation of the height of students at Lake Worth High School, my sixth period altitude class would be an example of a sample, okay? So then I would base my normal distribution curve based off of you guys. That would be an example of a sample. I would use this symbol to represent mean and this symbol to represent standard deviation. But if I wanted to do every single student in Lake Worth High School, that's my population. The symbols do change when you're talking about everyone versus a smaller sample. Does that make sense? Okay? They still mean this symbol right here. This one means standard deviation. I'm going to put SD for standard deviation. And this one here, it looks like a M with an extra tail on the end. This one does mean mean. Okay? So making sure you use proper, notation when representing this is always good. And this bell curve shows the breakdown of your data. The mean is smack dab in the middle, which splits your data into 50% to the left, 50% to the right. But when you have one standard deviation, that's what that -1S and +1S means. That means there's 68% of your data lies in between whatever those two numbers are. -2S, +2S, that's 95%. That means out of all the data that you collected from your sample, 95% of your data lies in between that number and that number. Okay, because remember, this x-axis represents the values that you're dealing with. Okay? Last but not least, you have 3 standard deviations, which is 99.7%. So almost 100% of your data, sometimes it is 100%, lies in between 3 standard deviations. Okay? If it lies outside of 3 standard deviations, that means that it is an outlier. Okay? So if it lies anywhere here, that means that it is an outlier. All right? So that's the breakdown. Empirical. Questions so far? This right here is pretty much just definition. Okay, before we get to some examples. That's all I explained right there. Okay? Now, do realize it is 68% of the data, 95%, 99.7% total from one standard deviation to the other respective standard deviation. But remember, the mean splits is straight down in the middle. So if you take that 68% and cut it in half, that means within one standard deviation in the mean, that's 34% on the left, 34% on the right. Does everybody understand where the 34 came from? You take 68 and do what to it? Divide it by 2. Okay, let's find out each other individual piece here. We're going to fill this out. Now, between 2 standard deviations, how much is that? 95%. Okay, so when I split it in half, What's half of 95%? So 47, now I'm just writing this just so that everybody can see this. This 47.5% in between two standard deviations and the mean, which means how much lies in between one standard deviation and two standard deviations? 13.5. So 13.5% of your data lies in between whatever that value is for the second standard deviation and whatever that value is for the first standard deviation. Came from the math side. All right. What about on the other side? Between the positive 1 and the positive 2? It still is 13.5%. This is symmetrical, so whatever it is on the left-hand side is going to be it on the right-hand side. Okay? Let's look at 3 standard deviations. What's the percentage? 99.7. So if I split 99.7 in half, 49.85 lies in between the mean and the third standard deviation, either to the left or to the right. So how much lies in between -3 and -2? That number. Which one is it? 2.35. 2.35%. Did everybody hear her? To get this value that's in orange, she took the 49.85% and subtracted from the 47.5%, just to get that little sliver in the middle. What about on this side? 2.35. So together, the orange and the blue numbers that are underneath the curve add up to be 99.7%. But there still is that little bit of percent that's to the left and to the right of the 3 standard deviations. And what is that number? Huh? 0.15. Now this is 0.15%. So that means that if something is there in that area, it has a less than 1% chance of lying outside of the 3 standard deviations, 99.7% of your data. Okay? You use those values. Sorry, let me go back. So, underneath your curve is 100% of your data. Okay? 100%. Now, you use this information to help you determine different percentages or probabilities of different situations happening, like you see here at number 1. At Smoothieville, yes, okay, it is Smoothieville. All right, at Smoothieville, the mean number of calories in a small smoothie is 420, with a standard deviation of 40 calories. If the distribution is normally distributed, what percent of small smoothies have less than 460 calories? Okay? Would it help to memorize these values? I would say maybe not these small individual values, but definitely the 68, the 95, and the 99.7%, because then you can always recreate this if you need to. Okay? So here's an example of a normal distribution curve. As you can see, the mean is straight down in the middle of 420, and then you see the 460. Clearly, it's going to be to the right of the x-axis because it's bigger than 420. And you're looking for the percent of smoothies that have less than 460 calories. So that means that you are looking for this amount or this percentage out of your data, okay? You determine what this is by figuring out, okay, 460. Is that 1 standard deviation away from the mean, 2 standard deviations, or 3 standard deviations, okay? If the standard deviation is 40 calories, and you recall from this chart right here, to get this value, you would just add 1 standard deviation to your mean. What is 420 plus 40? So right here, this represents one standard deviation away from your mean, which means on your bell curve, that is here and everything less than it. You see that? So to determine the percent of smoothies that have less than 460 calories, you basically are adding all those small little individual pieces, or basically just adding up whatever these probabilities are. No. If we add each one of these numbers, we won't have to worry about doing any type of subtraction. We'll just add those numbers because that's what's within that region. Yes, now we could add these three numbers and subtract it from 100, because then we'll get the remaining. No, it's a complement. Okay? Either way, we should still get the same answer. Okay? And the 0.15, yes, I do apologize. You also know the percentage of that. So you can do that as well. There's different ways to figure out what this percentage is. It just depends on how you look at it. Okay? So what is this percent? 84%. And again, you can either get that by adding all the yellow circles. You can add all the ones that are underneath that red curve and subtract it from 100. You can even take 50%, which is to the left of the mean, and then add 34%. You'll still get 84% no matter which way you do it. Okay? Question. Let's look at the next one. Okay? I just added this in here for the visual aspect of it. Okay? At a New Zealand zoo, 99.7% of the kiwi birds are between 2.6 and 12.8 years old. So that right there, 99.7% should trigger that represents what? 3 standard deviations. So it's basically saying that here, 99.7% of the kiwi birds lie between 2.6 and 12.8. So that means that this value is 2.6 and this value is 12.8. That's what that represents. Okay? So if the distribution is normally distributed, what is the mean and standard deviation? So this one, you're actually trying to figure out, okay, what is this value right here in the middle? And then after that, what is the spread? Okay? Now, if I'm looking for the mean, which is smack dab in the middle, yes, I need to add those two n values and do what? Divide by 2. The mean, right? You add the values and divide by 2, one in the middle. And this will give me my mean. What is that value? 7.7. So the average kiwi bird is 7.7 years old. Okay, so this is my mean. That's that value that's right here in the middle. Okay? Now I need to figure out what my standard deviation is. Any takers? But you got to figure out, okay, exactly how much am I adding to get there, and then to get to the second one, and then to the third one. I'll figure that out. Yes? Yeah. Everybody hear what she said? She basically said, well, you can take your mean value, you can subtract it from, either this side or the other side, and then divide it by what? Divided by 3, because it's 3 standard deviations away. Okay? Now, real quick, what if you got your mean wrong? We didn't, but let's just say you did. Then your whole problem's wrong. But there's still a saving grace. I can take that same concept, but not use an answer that I found just in case this part is wrong. There's still saving grace for this problem if we got the mean wrong. Divide by 6. That way, if you do get the mean wrong, you still have an opportunity to get the standard deviation right. By doing the same concept, instead of using the mean, we use the upper third standard deviation, subtract it from the lower third standard deviation, and then divide it by however many standard deviations lie in between them. That is 1, 2, 3, 4, 5, 6. What do you mean they're all different sizes? The realize that these numbers represent basically the years, the ages of these keywords. Okay, and so the distance between the mean and the first standard deviation will be the same. Yes, these actual weights or these actual ages will be different, but they'll still be the equal spread from each other. Because you're subtracting one standard deviation, subtracting two standard deviations versus adding one, adding two, adding two. What is this number? 1.7. Okay, so if I wanted to, from 7.7, I could add one standard deviation to it. I'm just going to make this a little bit bigger because my handwriting is just too big for this, okay? So if this is my mean, it's at 7.7. If I add 1.7 to 7.7, what do I get? 9.4. So that's one standard deviation. Add 1.7 to 9.4. 11.1. Add 1.7 to 11.1. And wasn't that the third standard deviation? So this right here would be the breakdown of just the right side of this normal distribution curve. Okay? To get the other side, I would, so what's 7.7 minus 1.7? 6. Subtract 1.7. 4.3. Subtract 1.7. 2.6. And wasn't that the third standard deviation on that end? So right here, this will be an example of the full completed normal distribution curve representing the mean and the standard deviation. So even using this, I can even ask you future questions to say, okay, well, what percentage of kiwi birds have ages between 6 and 9.4? And you would say 68% using what you know about the empirical rule and the percentages. See what I'm saying? Let's look at the next one. You guys got a hang of it? You want to try this one on your own? You want to do this one together? Okay. So it says the class of second graders has a mean height of 5 feet with standard deviation of 1 inch. Assuming the distribution is normal, so normal distribution, what percent of the class must be between 4'10" and 5'2"? Let's create the normal distribution curve for this. I'm just going to forget about that because, like I said, my handwriting is too big for this. I'm going to make my own. Always in the middle of a normal distribution curve is what? Which is 5 feet. To the left and to the right are going to be your 1 standard deviation, 2 standard deviations, 3 standard deviations. What's 1 standard deviation away from the mean? 5 foot, 1 inch. Because the standard deviation is 1, so that means you have to add 1 inch to each height before. What's the next one? 5 foot, 2 inches. Because you add 1 inch to the previous one. It's got to be based off of the information that you're given. So if the mean is 5 and the standard deviation is 1, you continue to add 1 inch to get to 1 standard deviation, 2 standard deviations, and then 3 standard deviations. What's the next one? 5'3". You wouldn't go beyond that because you only go 3 standard deviations. That is 98.5 No, so sorry, it's 49.85% of your data right here. Let's go the other way. 4'11", 4'10", and then 4 feet 9 inches. Is everyone understanding where these numbers are coming from? By adding one standard deviation to the mean to get to the right, subtracting one standard deviation from the mean to get the left. Now, if we look, aren't 4'10" and 5'2" on our standard deviations? Which one? On the 2 standard deviations. So right here, 95% of the class has a height between 4'10" and 5'2". Okay. I want you guys to try the next one on your own. If you have questions, please make sure you ask either myself or Brian. We're here to help where we with this problem. TVs from a particular manufacturer are found to last on average. Average means what? The mean. So on average, for 3 years without any need for service. So that means smack dab in the middle, the mean is going to be 3. And it says the standard deviation is 6 months. 6 months is how much of the year? So then if we can fill in the rest of this normal distribution curve. So what's one standard deviation to the right? Keep going. Keep going. And again, you just get that by adding 0.5 to each standard deviation because it says 6 months. 6 months is half of a year. On the left-hand side, we do the opposite. We don't add, we. So this becomes, and then. So when it asks you at least what percent of the TVs need service in less than 2 years? Well, here's 2, and it says less, so that means I'm considering everything to the left. So less than 2 years would be everything to the left. I went ahead and copied over the percentages from the other table or from the other chart. You guys could have done it any way that you see fit to find this percentage. But at the end of the day, the answer is what? 2.5%. And again, you can just get that by doing 0.15 and then 2.35. Okay? So far, how is this? Okay. Has anybody thought of any questions per se pertaining to this? Not even what the value is not on the standard deviation? That can happen. Okay? If you notice, for this particular example, what if I asked you, needed service after 3 years and 3 months? Okay, that's true because it is half. Okay, what if it was a little bit not as nice as that? Okay, what if it's something that you just can't, split in half? You'd be splitting in half for days trying to figure out, the respective percentages. Okay, how do you do this? It's not that bad. Not all values would be 1, 2, or 3 standard deviations away from the mean or easy to figure out in your head, like you guys can see on that one. That was a bad example. In order to determine percentages and probabilities for these problems, we must convert values to a z-score. Okay, the z-score, which is the formula that you see there, allows you to find the probabilities for any value. Okay, for any value. Now, if z is 1, 2, or 3 plus or minus standard deviations, then of course you use the empirical rule. What we're about to do does not apply if it's actually on a standard deviation. Okay? Only if it's not one of the standard deviations is when you do this. You have to use the table that I gave you. It's either on blue or it was on the goldenrod. So have that nearby because we're going to need this. There's also a calculator way to do this, but a lot of you guys don't have the graphing calculator, so we're not going to do that. Everything's going to be done by hand. So again, the formula is going to be used to find either standard deviations or means by solving for basically what we don't know. So on a physics test, a score of 98 is exactly 2.5 standard deviations above the mean. If the standard deviations of the test is 10, what is the mean of the test? Okay? So, we know a few pieces of information here. What's one thing that we know? You know that the standard deviation is 10. The standard deviation for the test is 10. Okay? So this right here represents S. We also know what? We also know that 89 is exactly 2.5 standard deviations away from the mean. Okay, we're going to have to use those somewhere within this formula, okay? We're going to start with this one because this is a sample. We don't know the mean because that's what the problem's asking us to find. So which part of this formula is going to be our variable? There's two x's in here. X with the bar. Remember, this represents mean. That's what we don't know. But we do know that S is 10, so I'm going to plug 10 in here. Now X. That X is the same X for that X-axis value that you're dealing with. What are we talking about here? What's this problem talking about? Test scores. So 98 represents a test score. What did I say, 98? Okay. 89. That is my X value. Okay? How do you know? Because since we're talking about scores on a physics test, that means that if I were to create the normal distribution curve, whatever the mean is, which is what I don't know, 98 is one of those values on the x-axis. That is exactly 2.5 standard deviations above the mean. Hence why I put it to the right, because it has to be above. And it's going to lie somewhere in between. Here's 1, there's 2, and then here's 3 standard deviations. So it's lying somewhere between that second and that third standard deviation. Okay? So that's how we know that 89 is F. Which means that this 2.5 is going to have to go in for Z. Okay? It's going to have to go in for Z. Everybody understand? Okay? So right here, it says if Z, right here, this is if we have empirical values. But if it's not exactly at 1 or at 2 or at 3 standard deviations, Z is still your standard deviation. So since it is 2.5 standard deviations above the mean, 2.5 is going to go in for Z. We are using this formula to help us figure out our mean because 89 is not exactly on a standard deviation. Other questions? It's pretty much here. Other questions? When do I use that formula? When it's not on a standard deviation, and 89 is not on a standard deviation. It's not on 2, it's not on 3, it's not on 1, it's on 2.5. So we're going to use this formula to help us figure out exactly what is our mean. So then that way, 89 will be exactly 2.5 above our mean. This turns into an algebraic problem. Yes? Because it's older. So like I said, it said that it was 2.5 standard deviations above the mean. So that means that here's the second standard deviation in the pink to the left. Here's the third standard deviation in the pink to the right. So it's lying somewhere in between them. How do I solve for the mean? Multiply by 10. What is 10 times 2.5? So 25 equals 89 minus the mean. How do I solve for the mean? Subtract 89. What's 89 or 25 minus 89? Negative 64 equals a negative mean. Mean cannot be negative. So then the mean is 64. Okay? So the mean is 64 for 89 to be 2.5 standard deviations above the mean. It's just a formula that you just plug in. The question. Yes. It's the notation to represent mean when you're dealing with a sample. The M that has the extra tail, that's known as the Greek symbol mu, that's used when you're talking about the entire population of students who are taking this physics test. Yes. To be honest, it's the same formula either way. So we could have used the other one, but considering that, like I said, we don't know for sure if it's the entire population of physics tests or not, then we just use the sample formula. So again, it's the same formula, just different symbols. Other questions? All right, let's look at example 6. Wait times at a new burger joint is normally distributed with a mean of 9 minutes. If Ariel waited 6 minutes and her z-score is -2, find the standard deviation. Okay? So, we don't know the standard deviation, but we do have a z-score. We do know how long she waited, and we do know the mean. So we can plug in our information into the formula here. What's z? -2. What is x? 6. What is x bar? That represents my mean. And I'm looking for s, which represents my standard deviation. What is 6 minus 9? -3. So all I'm doing is using the formula and solving the problem here. Okay? How do I solve for s? And then divide by -2. So what's -3 divided by -2? 3/2 or 1.5. We're talking about minutes. We probably want to go with 1.5 minutes. Yes. X represents in this particular example, X represents the time that she waited. In the previous problem, it represented the score on the physics test. Okay? So X represents whatever data we're talking about that we collected. So it's the same X that represents this vertical axis right here. So like in this case, this one represented the years needed for service. Now, 68% of the patrons live within what range of time? 68, that's a trigger percentage. The first standard deviation. So here's the mean of 9 minutes. So that means between this value, which I'm looking for, and this value, which I'm looking for, 68% of the data is there. How do you find out what these two values are? Add a standard deviation, subtract a standard deviation. So what's 9 plus 1.5? And what's 9 minus 1.5? And again, we know that because 68% is one standard deviation. And do mind you, this is about 68%, about 99.5%, about 95%, about 99.7%. Okay? The higher up you get in the math, those decimals start to increase after the numbers. Okay? All right. 7. Can you guys give it a try? Okay. So for number 7, it says the data below represents the cost of a small cone at 10 ice cream stores. If the standard deviation is $1.16, how many prices out of these 10 ice cream stores have a z-score less than 1.2? In this particular problem, you had to find actually 2 things prior to you actually answering the question. You had to figure out, what was the first thing? You had to figure out the mean. Because you were given the z-score, you were given the standard deviation, but you did not know the mean in order to help you figure out what was the price to get a z-score of 1.2. So to find the mean, hopefully everybody remembers it from like a long time ago that to find the mean, you just add. So you add all these and divide by 10. So what was the mean? 2.6. So now that you have the mean, you can figure out the x value, which represents the cost that has a z-score of 1.2. So x minus 2.6 over 1.16 should equal 1.2. When you multiply by 1.16, what do you get? 1.392. How do I solve for x? So x equals, so 3.992, or in other words, $3.99 represents the x value that has a z-score of 1.2. So if you're looking for the prices of the different stores that have a z-score less than 1.2, you had to count how many were less than $3.99. So that basically did not include these first 2 stores or these last 2 stores. So how many is that? So your final answer for this problem was 8 stores. Questions? That is using the z-score to help you solve problems. Okay? Let's go a little bit deeper. The number of oranges produced by an orange tree in Florida is 1,200, with a standard deviation of 60 oranges. If the distribution is normal, what's the probability that a random tree produces less than 1120 oranges? Okay? So, for this particular one, what information do we have? We got the mean? We got standard deviation? And what else? We actually don't have the z-score here. What's the mean in this problem? Yes, 1,200 is your mean, okay? So this right here represents x. You knew that because it says the number of orange trees produced by an orange tree in Florida is given to you there. So basically, you have 1,200, like that's data point. No, that's not a data point. That number represents your mean. And your standard deviation is 60, so you have your S. And for this particular one, you are looking for the probability that a random tree produces less than this many oranges. So then that represents your regular X. So on a normal distribution curve with the mean of 1,200, standard deviation of 60, you're trying to figure out what is the probability that is going to be less than 1,120 oranges. That's essentially what you're looking for. Now, if we do a little bit of math, what's 1,200 minus 60? 1,140. And what's 1,140 minus 60? 1,080. 1,120 does not lie on a standard deviation, does it? No, it lies somewhere in between these two. Okay? Not exactly at half, so we're going to actually have to figure out what is that probability. Now we do that by figuring out our z-score, okay? Because we have all of our pieces to find our z-score, and then we're going to use that to figure out our probability. So let's plug in, unless there are questions. 1120 minus 1200 divided by 60. What is that value? Oh, the top is negative 80 and divided by 60. Okay, then what's this number? Okay, for this, you only hear me say this a few times ever. We actually gonna need a decimal for this one. 33333. Okay, yeah, we actually need the decimal for this, and the reason why is because we need to use that table. Okay, and if you notice, the only thing that's on that table are decimals. Okay, this is a standard normal distribution cumulative table. This table helps us figure out probabilities. Okay, probabilities that are underneath curves. Okay, more specifically, these represent probabilities that are to the right, sorry, that's left, to the left of some particular x value, okay? You need to make a note somewhere near this table that these probabilities are based off of to the left of some particular x value, of any x value, okay? You determine what this value is based off of essentially what we're doing right now, okay? So we're looking for everything that's less than 1120. So when we go through and find out the corresponding probability, we found everything that's less than 1120. So the z-score was 1.333, correct? So what we do is we go to 1.3 along this side of the table, okay? So we find where 1.3 is. It's right there. Now the next decimal after the first 3 was another 3, correct? So then we go to 0.03 because together 1.3 and 0.03 make 1.33, correct? And so what we do, now don't draw on yours like how I'm about to draw on mine because I have several of these. You only have one. Okay, so kind of like guide along with your pencil where you need to go. What I'm basically going to do is I'm going to see where these two numbers intersect. Okay? Because where they do, actually I have it backwards. I'm so sorry. Fix this. It's the probability to the right. Sorry. Probability to the right. My mistake. And I was looking at that. Ooh, that's over 6%. So I couldn't remember. I apologize. So this number right here, this 0.9082 represents the probability of being greater than that x value. Okay? So does everyone understand? So if I go back to this problem, that value on the table basically told us that all of this is basically 90.82%. That's what that table just told us. Yes, because it was a probability, so you multiply by 100 to get to the percentage. Everything in the table was a probability, so I just multiplied by 100. That's how I got the percentage. But I'm not looking for the probability to the right. I'm looking for the probability to the and how much? How much is underneath a curve? 100%. So to find the orange, which is my answer, the answer I'm looking for, I need to take 100% and subtract it from 90.82%. So when it asks you what's the probability, a random tree produces less than that many oranges, it's 9.18%. It actually asked me for a probability, so I need to convert it back to a decimal. A fraction? That's percentage. Probability is actually a decimal. So help me out. I need to convert this back to a decimal. What is this? Yeah, so probability is a decimal. Percentages are where you multiply by 100. So that was my mistake. Yeah, yeah, we gave them the no, we only gave them that one side. So I know which one you're talking about. They won't have to worry about the negative. They'll just have to do after value if they run to a negative one, which they should. Yeah. Yeah. And that was my mistake. So I converted to percent. Questions? We're gonna do another one. We're gonna do however many on the page. Okay. Okay. So data was collected on speed of cars traveling near schools. The mean speed was 33 miles per hour with a standard deviation of 8 miles per hour. Out of 200 cars that drove by the school, how many were traveling at most 33 miles per hour? So let's take a look at the information that we know. We know the mean speed is 33, which means that it's going to be smack dab in the middle of our normal distribution curve. And the standard deviation is 8 miles per hour. Now, if we add 8 to 33, what do we get? Is what? So we get 41. Add 8 to 41. 49. And we can keep going from there. But if we notice, it says out of 200 cars that drove by the school, how many were traveling at most 45 miles per hour? 45 does not lie on a normal standard deviation. So we're going to have to figure out what that probability is. What's X? What's our mean? And our standard deviation is 8. What is Z? 1.5, which means that we are going to go to our table and we're going to take a look. We're going to go down that left-hand side, see where it hits at 1.5. And what's the decimal that follows after 1.5? So we don't have to go that far over. So we see that that probability is what? Very good. 0.9332. So that's basically telling us 0.9332. Is that talking about the area that's to the left or the area that's to the right of our X value? It is talking about our area to the left. And we know it's the area to the left because already 45 is to the right of our mean, which is 50%. So if this is supposed to be representing 93%, that means it has to be the area that is to the left of that value. Okay? So now that we know that, now that we know the probability, we can actually figure out how many of those 200 cars were traveling at most 45 miles per hour, because at most means either less than or exactly 45. So you actually have to take the probability and multiply it by the number of cars that you were looking at, which is what? 200. This right here, this process of taking the probability and multiplying it by the X value, or not the X value, the number that you're dealing with, is called expected value. How many cars? Was it a decimal? Okay. Give me the decimal. 186.64. Okay. So can we make up for that the 0.36 of a car? Okay, so in this case it's going to be 186 because we can't make up for, okay? If you do say 187, for example, I don't know, I'll have to talk to my coworkers to see if we're going to do this acceptable. Always provide the decimal answer before you round, especially when it comes to something like expected value. All right? The last two. The last two. I want you guys to try on your own. Last two, I want you guys to try on your own. Okay, let's go over these problems. So, the number of hours that Jake plays Minecraft per week is normally distributed with a mean of 24 and a standard deviation of 2.5 hours, with the probability that next week you will play Minecraft over 1,620 minutes. If you notice, you're going to have to convert this to hours. How many hours is that? 27. So you do need to convert that to hours, otherwise you're not going to be able to work on this problem. You need to make sure you have the same units of measurement. So if the mean is at 24 hours and we're trying to figure out if he plays over 27, that means you're looking for this probability right here. Okay? So we plug everything in. We need our z-score. What is x? 27. What's our mean? We're going to divide it by? 2.5. And our z is what? 1.2. So that means on our table we have to go to 1.2 and 0. So then we get this 0.8849. Now is that more than 50% or less than 50%? More. It's more. So basically that 0.8849. Is that, was it 49? Yes. Okay, so that 88.8849 represents this part right here. Again, you know this because 27 is more than 50%. 88 is more than 50%. So that probability is representing what is highlighted in orange. How do you figure out what we actually want to find? So then we'll find our probability, which is what? 0.1151? Questions? Now let's look at the next one. Alyssa doesn't seem to have pretty good luck with goldfish. The length of time before flushing is normally distributed with a mean of 42 days and a standard deviation of 8. She buys new goldfish on January 1st with the probability that it will live longer than Valentine's Day. From January 1st to Valentine's Day is how many days? It's 45 days. So if the mean is 42, 45 is going to be to the right of this, and we're looking to see if they live longer than Valentine's Day, which means that it needs to, am I shading to the left or to the right? To the right, because longer will be more than that. Okay? So a similar process. Let's go through it. Z equals what? 45 minus 42 over 8. The Z value is 0.375. Now, when you go to look at the table, you will see that there is no 0.75 option, okay? Or 0.075 option. So what do? You go over to the 0.3, and then you go to the 0.07 and the 0.08, and do what with these two numbers? You add them and divide by 2 to figure out the average to get 0.075. So when I add 0.643 and 0.6480 and divide it by 2, what do I get? Okay, you're going to have to say that one more time. Now, is that going to be the probability to the left of 45 or to the right of 45? Again, it's more than 50%. So this represents this. How do I find the blue shaded? Subtract that number from 1. And what do you get? Is that right? Yes. Yes. 0.073. Well, in that case, well, I probably won't give you nothing like that because you're going to need to go a little bit deeper into the division process of that. We'll save that for graphing calculators. Yeah. The reason why this particular problem was shaded to the left, where am I? Because it was asking if the probability of them living longer. So we weren't concerned about this orange area because that basically represents the probability that they won't live to Valentine's Day. We want the probability that they will live longer than Valentine's Day, like St. Patrick's Day or to April Fool's Day. Oh no. The table represents a probability. You're gonna have to decide whether or not that probability from the table is gonna represent all the area to the left or the area to the right of that line. Okay? So that's why it's always good to have an idea of where the mean is, where is the x value that you're trying to determine, so in that way you'll know whether or not you're going to go to the left or to the right. Okay? Any other questions on normal distribution? Does everybody understand where you would need to multiply by your x value, like how we did in number 9? The only time you're ever going to multiply is if you're actually trying to figure out a particular number. Okay? So be careful not to use your sample as your x value. All right? Other than that, make sure again that you also know your z-score formula that is used to figure out probabilities using your table or to help you in the process of finding a mean or a standard deviation, as well as the breakdown of the empirical rule, your 68, 95, and 99.7%. Okay? All right.